So, well, firstly, hello everybody, because we are in this way. It's not, I don't know, it is morning, good afternoon. Also with application of clay, but in this case, clay-based Bionanocomposite fields, also for application related to the skin, to protection of the skins. I will introduce two types of Bionanocomposites. One is the system. Actually, this is the article we have for publication in the special issue. Is centered in the Bionanocomposites based on the intercalation of gentamicin antibiotic in monoionite and then combine it with hydroxypropyl methyl cellulose, which is called a typical Bionanocomposite. And then the second part, I will introduce another type of biocomposite systems that actually is a multi-component material in which different type of nanoparticles are combined, and then it can be also regarded as a possibility to be used in this type of application. Why we will use clay-based system for wood threshing application? Well, we know that there are many animals, especially like elephants, bees, or hippopotamus, that use mud for protection of their skin, and also because sometimes they have other type of role, like antiparasitary things. Human beings have also used for a long time clays and so for applications for treatment of the skin, typical mask based in different type of clays with different colors, like Linda said before. We have variety of clays and with different components that may also have important roles for other activity when used. That can be used sometimes for producing cataplasms, and so have a different type of effects, like the ulcers that Linda talked before, which is just because of the clay. But where sometimes it is possible also to use the clay or other materials in which we could put also an active principle that can be important to deliver these properties of activity against whatever is the microorganism we want to treat. So it is typical, these are the so-called typical controller dye systems in which we can use this type of system for applications in food, in agriculture, but also in cosmetic and in pharmaceutics. That is the part I will introduce today. And the role always of this system is to produce, to control the dosage of the active principle in the system. So we have sometimes we want to regulate, especially to reduce toxicity, because sometimes these drugs usually are very, could be dangerous if they are in excess, and also because we can produce the so-called perfect level for have in the system the effective amount that we need for the treatment. What kind of particles have typically uses in this application? There are different types from biological origin, like liposomes or cyclodextrins, but there are also inorganic systems like metal nanoparticles or metallocide nanoparticles, more complex systems like moss or silica, mesopolysilica. But especially we are focusing in the use of clays and biopolymers, not alone but combined. That is the samples I will talk today, and that leads us to the use of Bionanocomposite. Bionanocomposites are in systems in which is a nanocomposite in which the polymer we are using to produce it is a biopolymer. These systems are known from not too many years, maybe 20 years ago, it started to develop Bionanocomposite, but they are very interesting for numerous applications, especially because the use of the biopolymers incorporate biodegradability and biocompatibility. So applications that can be related to the preparation of bioplasticos or foams for isolation or removal of pollutants, but there are also other applications of these systems that deals with biomedicine. For instance, the preparation of scaffolds for tissue engineering, or the immobilization of virus to produce new vaccines. Also, there is important and many applications dealing with the development of new controlled drug delivery system, even targeted applications. I think there is some talks later on that will enter in these applications. Mine are examples, but I will focus it on application related to bone healing. These are examples in which you use just the clay in combination with the polymer, because the clay, as in the sample we heard in the talk before, can have these antibacterial properties. But also sometimes it's important because in this system is possible to immobilize other type of bioactive species that can provide to the targeted application. One thing we have to keep in mind is when we use bionanocomposite in drug delivery, but for treatment of skin disease or kiss wounds, is that the application is different than when we have a typical drug delivery system for oral drugs. In this case, because the treatment will be topical, we need to be aware of how is the local concentration of this bioactive principle, in general, for instance, antibiotics, because when we treat the drug, we don't have we need very small amounts. But when we have in a topical treatment, sometimes we need larger amounts to be effective and also to keep this effectiveness for longer time. So that is the important point when we have to control how is delivery system. One of the most typical antibiotics that have been tested or have been studied for this application is gentamicin. Gentamicin is an aminoglycoside antibiotic, and this is important. This is the presence of amino groups that can be protonated and then give possibility for interact with the different substrates that can be used for its delivery. And in fact, gentamicin and clays have been different studies. In our paper, in common paper, we have the first part in the introduction. We have made like a small review of all the at least more practically all we have found of papers dealing with the combination of gentamicin with clays that can be from kaolinites to smectites or halloysite also, or even biodegradable hydroxides, especially to introduce in the system antibacterial properties. This is important and relevant when combined with biocompatible polymers, because this can be used to provide bioactive coatings, especially for application in implants and scaffolds. These are the main applications. Other applications may deal with the preparation of hydrogels, which is a little related with the example we heard before, is to apply directly in the wound. So in the first example, I will show you is the combination with a biopolymer, just a classical bionanocomposite, in which we have selected hydropropyl methyl cellulose as biopolymer. Why this ternary system? Where we try to incorporate in this, we chooses this biopolymer because it's highly hydrophilic, which means we will be able to have a system in which we will have water and we can have release of the antibiotic, or make it more stable and accessible for the application, for the activity they have to have. And also the use of the clay is necessary because hydroxypropyl methyl cellulose is a biopolymer with which mechanical properties and especially its stability in moisture is now too high. So the presence of the clay may improve their properties, mechanical properties, and also to have stability when it is prepared as a film. So in this example, we choose a common clay. We can try others with especially smectites because they have exchangeable cations. And then this is our idea is to incorporate the gentamicin intercalated in the clay. However, we have to think why we will intercalate this antibiotic in the clay. Well, it's because, as I told before, the gentamicin in water become protonated. There are several points or several alkyl groups that can be protonated depending on the pH. But in general, in the typical pH on water, when you have the clay, usually you are in the 5 or 8 in pH, and there are typically 5, 4, or 3 possibilities to protonate. I mean, three positive chair, 4 or 5 positive chairs in the molecule. This is interesting because that create electrostatic interaction with the negatively charged clay, and then it's possible to stabilize it in the interlayer region. Well, we performed a typical classical but systematic absorption isotherm study. This was not reported before, even though there are many samples, nobody studied how you control what is the driving force to produce this intercalation or this absorption. And we observed that this is a spontaneous process in which more or less is absorbed practically at the beginning all the antibiotic in the water, and then you reach a plateau to saturate the clay in absorption of the polymer. The amount of gentamicin you are able to absorb is about in the range that could be, especially when you remove the part that is possibly absorbed at the external, I mean there is no well retained, is practically if you have absorbed the molecule when we have 5 charge, and then is practically the capacity or exchange of our clay we were using in this work. It's great diffraction pattern, so that is intercalation because they are the displacement of the first reflection peak to lower the 2 theta angles, and then we observe that when we increase and when we have this shift in the angle, is related to the intercalation of the molecule, organic molecule, because the sodium content in the clay decreases. Actually, if we consider what is the possible structure or the possible arrangement of the molecule in the interlayer region, it corresponds to a monolayer of intercalated molecules. More or less, it's not completely flat because these rings have a certain conformation, but it's practically flat, layer and flat, parallel to the silicate layers. There are interactions. In fact, from the FTR spectra, we confirm that the protonated antibiotic is preserved and this is stabilized in the clay when it's absorbed on the clay, and this the material is very stable. It's so stable that the release is very slow release. And for instance, when we put in water, or when we have just the material just prepared by absorption, we were able to in 24 hours to release a certain amount. But when we use intercalated compound that had been previously washed, practically there is no desorption. This desorption could be promoted when we have in the medium other components like BBS, typical BBS concentration, very low, pH 7. It's possible to have some certain release of the antibiotic, which is good for the application. Because we want to immobilize this in the hydroxypropyl methylcellulose, we had tried also to put this in water for the preparation. So it's important to know before, if we were releasing the antibiotic before we prepared our bionanocomposite, which is not the case. We were using different, we had the possibility to prepare different type of fields that are very good, very good and very good aspect, and are very easy to prepare just by casting method. And then we can use different hybrid intercalation compound with different content in gentamicin, but also we can vary the amount of gentamicin in the film depending on what is the proportion between the biopolymer and the intercalation compound. And we have a very large range of content for preparation. So this means we can prepare bionanocomposites with different composition, which is good because the properties sometimes would be the better. So we can play with this to have the material. This is the aspect at the microscope, is kind of electron microscopy. And this, there are good, this biopolymer has 50%, more or less 15% of intercalation compounds. So it's large amount than this one, which is very small amount. And this is more homogeneous, but here we are able to see how is the clay. But the film is very consistent. The film has good mechanical properties improved by the presence of the clay. Well, it's brittle because always when we put these inorganic compounds in the clays, in the polymers, sometimes we decrease the elastic properties. And what is important for our application, we observe that there is the hydrophilic character of the material is practically the same, even when we incorporate a certain large amount of the hybrid material in the polymer. What is the effectiveness against microbials? Well, we tested for what is the typical Staphylococcus aureus, which is typically present in the skin infection. And we observed that for all the material we have tested, the effectiveness is very high. So it means we can reduce the dose of the required antibiotic by just using one of the fields in which we are incorporating very small amounts of gentamicin. So it's active, even if it's not quite easily released from the material, is very active. In fact, the activity is good also against other microorganisms, is that maybe the lowest is against the methicillin resistant Staphylococcus aureus is the one, but you don't have such a good results. We have certain activity that is not really high, but for the other ones we have tested, this is very effective. Which means this system could be a first step in the preparation we need to follow with application or with test in animals or something like this. We don't have yet done this. The second system I will talk today is a different one of type of bionanocomposites. This is also a ternary systems, but in which we had combination of 3 types of nanoparticles. We have two clays, sepiolite, which is allow us to have very good dispersion in water. And we have halloysite nanotubes that in this case we were using as containers to incorporate our active elements for the application. And then we have cellulose nanofibers. We will combine this and we will produce like a nanarchitectonics material, which is called, well, actually is like a nanostructured particles that are formed by combination of the three particles. And well, this is just to remember you that for those not familiar with, this is the aspect of the size of the of sepiolite are fibrous. And then we have the nanotubes of halloysite, which are a little wideness in the, but probably is shorter in length. And I do not have here, and sorry, in the picture I forgot to put a picture of how looks nanocellulose. Nanocellulose is quite similar in aspect to sepiolite. So in fact, there are 3 like a filamentous components of particles that can become combined. How? Well, we recently have shown that it is possible to assemble sepiolite and halloysite nanotubes just alone, the 2 of them, by using ultrasonication technique. In this case, we are able to stabilize a halloysite in water, very stable suspensions that may remain there for a long time. Also, this can be also used for preparation of different type of processed material, like films or forms. More importantly, with this methodology, we have also observed that it is possible because we have previous work related to the use of sepiolite as a stabilizer of this of different type of material in combination with other type of nanoparticles, such as cellulose nanofibers, carbon nanotubes, or graphene nanoparticles, or later on we have also tried layered double hydroxides of different type of nanoparticles and other components. This is the idea we have when we try to combine the 2 clays and the other 2 systems. So we prepared this combination, and we were able to have films when we have the three components with nanocellulose also, and so we can prepare like so-called hybrid nanopapers. These materials is it's important. They have very good mechanical properties, even better than if you have just films of nanocellulose alone, which is the element that produces the continuity. We have very homogeneous films that we by microscopy, and we have a hydrophilic character that is, in this case, is not preserved any of the components. In fact, it's our additive property. And so this kind of system, we can use, as I said before, the halloysite nanotubes for incorporation of the active or bioactive molecules. We choose, for instance, ibuprofen and sodium salicylate, and we were able to prepare materials in which the drug is loaded in the halloysite, and then the halloysite is combined with the other two nanoparticles materials. Like this, we have systems that can liberate, that can deliver the active bioactive molecules. And in fact, when we have the three components, the films, we observe that this release is more controlled. It's not like in a few minutes, we are able to lose almost all the elements that are in the halloysite nanotubes, but we have this type of slower release that give us the possibility to prepare systems for drug delivery, more controlled drug delivery. In fact, we check it and we observed that we have antimicrobial activity of this Bionanocomposite. We also observed that in this case, the activity was tested against S. aureus, against also E. coli, but E. coli didn't work so well because of the active bioactive principle we are using here is salicylic acid is not active for that. But in any case, this is the first approach in this application, and we think we can in the future try to go further and to have more specific applications. So finally, just for concluding some my talk, I just want to show you that today I tried to introduce two types of bionanocomposite systems that can be used for wound healing applications. In the first one, we process it like in a classical method, that the preparation of films with combining the clay with the active principle in a biopolymer. And in the second case, we are trying to prepare a more sophisticated system, but that give us more opportunities perhaps in the future to develop more specific system for applications in this type of health uses. And finally, some acknowledgement to other people that collaborate in this work in different parts of the world. Thank you, everybody.
Thank you very much for this excellent presentation. Questions are very welcome. Please ask.
Hello, Pilar.
Yeah.
Excellent presentation and work. I just feel curious. You're using gentamicin for the monomer light, but the latter part you're using the sepiolite and the halloysite. Is there any difference between the the different polymers for the incorporating the gentamicin?
In the second one, you say the second one. In the
yes.
second example, we just tried, because it was the first work we were using. Actually, we were just trying to see if this was possible to have the release from the halloysite nanotubes. And so we choose one example that was already published of some species already loaded in the halloysite. So that was the reason we didn't go for a specific or more large application, just to prove that it was possible to load the halloysite and then to prepare, because we were using ultrasonication. And as you've seen in my presentation, when we have the halloysite nanotubes loaded, we have to use ultrasonication, but in a bath, not in the very high energetic ultrasounds method that we use it for the preparation of just the films at the beginning. So because the drug, is inside the container, we didn't block it, the ends of the nanotubes, so it was possible that the drug was released. So that's the reason. But I think this system could be very promising for this. And also because we can use it for combining with other things. We have tried for other application combination with biopolymers and other nanoparticles, and it's very versatile. So this is the first step, and I think it could be very interesting in future.
Yes, but I don't know which one is the best one. For example, monomer sepiolite, halloysite is the
that
best
is the
one.
application, but you know, you have to choose, because when you when I work in the drug delivery, you have to choose and to try which is the application. In the case of the halloysite, I don't know if someone has tried to stabilize gentamicin. In sepiolite, I think there are some works, but no, it could be immobilized because it's protonic. So it could be immobilized. But the problem with sepiolite is that when you try to incorporate some drugs, the interaction is very strong, and the problem is to release this. Maybe for this application, it's not bad, but we didn't try.
Okay,
sorry. The example we use, this is I tried to combine two things here. It's not related the two approaches, you know. It's not was not intention in this talk, but it could be possible to use sepiolite probably.
So do you mean the gentamicin have been introduced into the interior space of the polymerase?
Yeah, and sometimes many of the words that people have published, sometimes they use, for instance, they want to try to prepare biofilms, and they use layer by layer. It's the most common methodology. You put a clay with a negative charge, you put the gentamicin in protonic form. So you were using layer by layer to create, and this is the typical application that people have done for this. There are also publication in halloysite with the gentamicin. I think is Raúl Franklin. I think it's your group or something from your group has done something with halloysite, I think, and gentamicin, I think.
We didn't work with gentamicin.
No, you didn't know. With someone, I learned something about halloysite. I thought it was your group, which is maybe it's another Russian group. So yeah, I think people use it kaolinite also, but it's because they are trying just to produce the biophase, no other things.
Okay, thank you, Pilar.
Thank you.
Any other questions, please? We have a question from the chat. Could ultrasonification potentially damage the crystalline structure of the clay if the energy input is too high? This comes from Kyle Hilsabeck.
Yeah, it's as I said, we didn't observe if you have a strong and very for a long time that we use pulse irradiation, and usually the problem you have is made by disaggregation. It's the same when you prepare for TN. And you can, in sepiolite, for instance, you can cut the length of the fibers. You cut the fibers, so you may have shorter fibers. That's possible, but the crystalline structure, I don't think so. It's more you just break the particles, but this is typical in ultrasonification preparation.
I also have a question.
Sorry? Another?
Did anybody want to ask the question? If no, I have a question. When you mix halloysite, sepiolite, and cellulose, how uniform is the mixture? Is it possible to somehow control and ensure that if you have a film made of these three components, in every part of this film, you will have exactly the same ratio of all three parts, because they are quite unstable. And I mean, if you mix them in water, some of them will settle down fast and so on. So did you study the uniformity of these films?
We think, especially the suspension, are very stable. We can keep them for months, and they are stable. When you have a segregation of phases, that could happen. For instance, we observed some of the sample we prepared with sepiolite and double hydroxides, and after some time, maybe or with more smectites, we have certain disaggregation. But this is possible because actually the thing is that sepiolite in water, you create a gel in which you were able to disperse the other nanoparticles. So actually, it's like you have a network, like inside you put the other particles. So more or less, they can be well disaggregated at the beginning. So when you dry this, you get samples that are very homogeneous.
Okay, thank you.
In fact, with nanocellulose, it's difficult to see in the microscope which one is sepiolite and which one is nanocellulose.